Many multiband wire antenna users remain unaware of the patterns produced by their antennas on different bands. So I'm going to kind of focus on that in this presentation. I think it was Terry Martin gave a nice talk on low-cost wire antennas on the CT Sarah website in their YouTube feed. So you may want to watch that if you haven't seen it before. It's a very nice presentation. For this presentation, I'm listing the main sources that I used as the basis of it for some solid technical information. I started with the ARRL antenna book, which has a lot of really good information. Sometimes the ARRL has it on sale as a download, and it's well worth getting if you're a big wire antenna aficionado. Then I refer to LB Cebik a lot, W4RNL, who's also deceased. He's deceased. He wrote numerous articles on antennas, was an ARRL technical advisor and antenna authority. The QEX editor called him probably the most widely published and often read author of amateur radio antenna articles ever to write on the subject. Then I refer to Joel Halas, W1ZR, who sadly is deceased now. He was the QST technical editor and a very prolific author of QST articles and ARRL books. Owen Duffy has a blog at owenduffy.net. I call him the Mythbuster. He's quoted in the ARRL antenna book on efficient end-fed half-wave matching transformers and various antenna topics. I've corresponded quite extensively with him on transformer modeling. So he's a really sharp guy. Then there's Steve Hunt, who's a hex beam expert at a website Karinya.net. I think Karinya is some sort of living in hut, but he has a lot of good technical topics on his website, which still lives on. I've also done a lot of my own simulations using EasyNet Pro Plus, which is now free, written by Roy Llewellyn, W7EL. And I've done a lot of work with SimSmith and SimNet 1.2, which was written by Ward Harriman. And I have corresponded a fair amount with Ward many times, and I identified several bugs in the software to him, which he has since fixed. I plan to learn some other tools, which I haven't done yet. MMANA GAL is another antenna simulation tool. I would recommend, if you want to learn something, use EasyNet Pro to start with. They both have their pros and cons, but I think there's a lot more models available with EasyNet Pro Plus that you can download from the web. And the ARRL antenna book also has some EasyNet downloads as part of the package. I will say that simulations are only a tool. The proof is in actual measurements which validate the simulations. It's very easy to go wrong and trust the simulation too much, but it's certainly a very useful tool. Okay, the main topics I'm going to talk about are some introductory stuff, Cebik's favorite backyard antennas, including if he only had one simple wire antenna, which is a 40 to 10 meter with known directionality. Then some definitions, some details about dipoles and multibanding of dipoles and doublets and multibanding of doublets, some feedline considerations and some antenna tuner considerations. First subject is, how do you narrow down which simple antenna to use? I think everyone realizes they're operation dependent. If they're for home use, you have more flexibility. You could have a semi-permanent installation, spend more time installing it. You may have more real estate than in a portable type operation, more mounting options, etc. For field day, you need some moderately quick deployment, making use of available mounting provisions, which may be very good or very poor. The big problem with field day is if you have multiple setups co-located, interference is an issue. So you have to worry about that. For parks on the air, you want it portable and lightweight with very quick deployment and limited mounting provisions. Some porta guys will go to half a dozen parks in one day or more. So it's very important to have quick setup capability, but with a decent performing antenna. Summits on the air is along the same lines, but even more portable and even more lightweight. And the expeditions, you want good performing antennas, and you have a reasonable amount of time to set up, somewhat comparable to field day. So you may have your favorite antenna in mind, but you may not be able to use it, depending on where you're doing it, the type of operation, and the environment that you're trying to operate in. Okay, I thought I might put up this slide. I just was comparing antennas just on a pure gain standpoint. First, let me give you a definition. dBi, dB isotropic, is dB with respect to an isotropic antenna, which is a conceptual antenna that radiates equally in all directions in a spherical pattern. So 3 dBi, for example, would be twice the power of an isotropic antenna. 6 dBi would be 4 times the power. 9 dBi would be 8 times the power. Every 3 dB doubles the power. So now let's just compare some antennas, which kind of really surprised me. The gain of a quarter wave vertical with a decent amount of radials over average ground is only 0.22 dBi at about a 22-degree angle. Not much better than an isotropic antenna. The gain of a dipole in free space also isn't great, but you never have it in free space. It's only 2.15 dBi, or about 1.6 times power of an isotropic. Now we start having some real gain. The gain of a half-wave dipole above average ground and half a wave above the ground is 7.9 dBi. That's pretty good at about a 28-degree angle. That's like 6 times the power of a isotropic antenna. And what about these specialized antennas, such as an extended double ZEP? A double ZEP, which is 88 feet long and 35 feet high on 20 meters with average ground, gives you a whopping 10.5 dBi or so at 28 degrees. That's 11 times more than isotropic. And a horizontal loop, which is a great antenna, say it's 560 feet long, about 70 feet high. On 20 meters, that's 12.9 dBi. That's incredible. At a nice DX angle of 12 degrees. So there's a wide range of powers involved in these different antennas. And if you notice, there's something pretty interesting. The gain of a dipole, halfway above ground, is quite a bit more than a quarter wave vertical, quite a bit more. So how could a vertical work at all? So this next slide shows why it can work. Its power is actually about 6 times weaker than a dipole mounted at half wave high. But the answer is, it's all about elevation angle, and elevation angle. Many backyard dipoles are just mounted too low with a near vertical incident skywave type elevation pattern. For example, let's take a 40-meter dipole mounted 35 feet high. That's a little better than a quarter wave. You take the same vertical, which is 33 feet high. It will do better below about 17 degrees. If you look at these plots, which I made, by the way, with EasyNeck, I digress for a second. If you want to play with EasyNeck, a lot of people don't know it, but you could actually save plots. You could make an azimuth or elevation plot for a particular antenna, save it, load up a new antenna, look at its plot, and then load up the one you saved. And you can plot multiple plots from different antennas in azimuth and elevation. Well, if you look at this, an antenna a quarter wave high is basically a big blob which is radiating mostly straight up. If you go down to or up to a half wavelength, now you start seeing a nice pattern. The main lobe drops down, and you could see that it's very efficient. If you look compared to a vertical, and this vertical could be a decent vertical with 16 ground radials. For high elevation angles, a dipole halfway high will beat it. But for low angles, surprisingly, less than about 17 degrees, the vertical will actually beat out a half-wave dipole mounted half a wavelength high. I'm sorry, I was talking about the quarter wave. The quarter wave will not do as well, quarter wave high dipole will not do as well as a vertical. In fact, below about 17 degrees, the vertical will do better if you forget about polarization, which is this whole separate thing. So that's why a vertical can work well for DX. In fact, there's companies like DX Commander that sells antennas trying to tout how wonderful verticals are. And they can be good if comparing it compared to a dipole only a quarter wavelength high. So now let's talk about some multi-band wire antennas in no particular order. Cebik's favorite backyard multi-band wire antennas with a dipole doublet, which is basically a dipole at the lowest frequency of operation, and then using an antenna tuner operated on all its harmonics. Then there's a broadside doublet, which is different in that it's based on the highest frequency of operation, and it's 1 1/4 wavelengths long at the highest frequency of operation. And then you go down by a factor of 4 to cover 4 bands. The advantage of that one is all the radiation is in the same direction. The dipole doublet has lobes. As you go up in frequency, you develop more and more lobes. He also likes the fan dipole because it has nice low SWR across the band, and they radiate all in the same direction. And it's suitable for use with a triplex, or if using a triplex of a field day. Then there's the loop antenna, which he likes a lot, and the inverted L. And if only he had one antenna, he likes the 44-foot doublet, covered 40 to 10 meters with known direction. Now let's talk about a fundamental fact about all horizontal antennas. And this comes from Cebik. The lower the antenna is a function of wavelength, the lower will be the overall gain, and the higher the elevation angle of the radiation. Now, you can't always do that. If you look at the half wave height for 80, 60, 40, and 30, those things are unmanageable for the average ham. Even 30 meters, the half wave is about 46.5 feet high. Very difficult to do for most hams. So you got to do the best you can. But a good rule of thumb to keep in mind is that if you could pull it off, height should be at least equal to the width of an antenna. And when you're doing that, you get a good radiation pattern because it's a half wavelength high for a dipole. And again, it's difficult to do with the lower bands, but do the best you can. So think in wavelength, not in feet, not in absolute feet. The relative amount of percentage of wavelength above ground is what's important. Now, I bet a lot of people don't know this. What's the difference between a dipole or a doublet? And I always wondered about that myself. Well, the answer is there's actually no formal difference. These are just two different names for the same antenna. According to the ARRL antenna book, the term doublet is often applied to symmetrical center-fed antennas that are not resonant or that are used on multiple bands to distinguish them from the resonant center-fed dipole. This is a matter of convention only. So I'm going to use that convention in the rest of the presentation. The figure in the upper right is a dipole. It's typically fed with coax, and it's recommended that you have a current balance at top for a better balanced antenna pattern. You can feed it with either 50 or 75 ohm coax. The impedance of the dipole is about 72 ohms. So 75 ohm coax is actually a better match, but either one will work fine with no problem. It's unbalanced feed, which is a nice advantage. The doublet, which is really made for multiband operation, it's fed with balance feed. It could be ladder line, which could be typically 300 or 450 ohms, or open wire line, 600 ohms, with a balance feed and an antenna tuner. Now, for driving a dipole or a doublet, the dipole has a big advantage of no tuner or built-in touch-up tuner, which is typically 3-to-1 VSWR capable. The doublet, on the other hand, needs a wideband antenna tuner, and this one showed a resonance on the lowest frequency of operation, but it doesn't have to be that way. Okay, let's talk about some antenna patterns. And again, I did this with EasyNet, and I saved the plots and reloaded plots from different EasyNet antenna models. When you're at half wave, the antenna pattern is pretty nice. When you go up to 3/4 of a wave, the antenna pattern is also nice. You start developing a small vertical lobe, which is not very important. When you go up to a full wave, everybody seems to say, at least some of the experts like Cebik will say, make it as high as you can. I don't know if that's really necessarily what you want to do, but let's assume he's correct for the moment. What happens here at a full wave is that in elevation, you get a main lobe which is at a lower elevation angle, so it's good for DX, but the lobe gets a little bit narrower, you'll notice, and you get some lobes which are kind of going off at 45 degrees, and they're pretty big fat lobes. So going up to one wavelength doesn't make a particularly pretty pattern. Yes, these lobes are great for DX, these low angle lobes, and you'll work other people at higher elevation angles. So for field day, for example, you'll work people that are relatively close and people that are relatively far away because of the different elevation angles. But this is not aesthetically pleasing. So a half wave or 3/4 wave, if you could manage that, you're doing quite well. And in azimuth, what happens is, if you're only a 1/4 wave off the ground, it looks pretty omnidirectional. As soon as you get half wave off the ground, you start getting the hourglass shape. And as you get higher and higher off the ground, the hourglass gets narrower at the center, which is generally a good thing. You tend to have more rejection off the sides. Let's see. That's basically all I want to say there. Now, how can we take advantage of a dipole's nice properties of directionality and somehow trying to expand it to multi-band operation? And why would we want to do that? Well, for several reasons. It'll maintain wide bandwidth of a standard dipole. It'll have a broadside radiation pattern on all bands. And it eliminates some of the system stresses you might have with other antennas requiring a wide range tuner, sometimes transformers or balance, and high VSWR. So you're eliminating those potential issues. They're also amenable to use with a diplexer or a triplexer for field day. If you want to put up one single multi-band dipole of some sort, it'll work with a diplexer or triplexer. It could be flat top or inverted V. And I'll talk about some of the approaches as we get further into the discussion. Now, here's a trick that I think very few people know about, but is great. I think hams over the years have always tried to take a 40-meter dipole and use it on 15 meters. And it never really worked out very well because there's a phenomenon called an end effect, which it's caused by the high voltage, low current at the ends of an antenna, at the ends of a dipole, which have no place to go but ground other than radiation. Most of the radiation comes from the high current point at the center and less radiation at the high voltage, low current points. So what happens is a dipole antenna tends to be shorter than what you would think based on the speed of light. So you make it shorter and fine, it's in resonance, great. Now you're trying to operate on 15 meters, which is the third harmonic. Now 15 meters will be way too high. It'll be probably outside the band. So people have tried to compromise by putting it sort of partially between the two and live with a bad SWR on both bands. Well, there is a nice trick. You basically go about a third of the way into the 40-meter dipole, and you solder on some stiff wire, about 2-foot long pieces. And you could make those into a loop. You twist the loop in the middle to form a figure 8. And you could solder it on. And then 40 will still be resonant in its band, but on 15, you can play with the wire loops, make them bigger or smaller, and put the resonance where you want it to be. And I actually ran some simulations here that show, golly gee, it actually works. What a really simple, nice way to have a dual band antenna with very little work. I also found another way to do it is to put a capacitor in series with one of the legs of the dipole. And it turns out it's about 270 picofarads at 2 kilovolts with a bleeder resistor across it for static discharge. And that works also. I also simulated that. And that is used very often for some other antennas to effectively shorten the antenna on its lowest frequency and not affect the higher frequencies. That's used typically for antennas such as an off-center fed antenna. It could be used in end-fed antennas, wherever you need to take the lowest frequency of operation and raise its frequency up without affecting the higher band. So that's kind of cool. All right, another way to get 2 antennas for the price of 1. Joel Halas wrote a QST article on using ladder line to make a dual antenna. He basically takes the lower frequency and wraps it around on the top and then just couples it into the shorter antenna. And I show here an antenna that will cover 40 meters and 20 meters. And you want to still have some sort of choke balance on the feed line. You could make that with ferrite beads. And there were several QST articles and QST feedback and in-depth stuff if you want to use other bands, any 2 ham bands. And this will actually have higher gain than a standard 40-meter antenna or a 20-meter antenna, all on one antenna with low VSWR. So that's kind of a cool antenna. And if you have 2 other favorite bands, there are dimensions available to make that. And by the way, you could make this into a 3-band antenna by using that capacitive hat trick that I just talked about. Take the 40-meter antenna, go about a third of the way in, solder a piece of wire onto it right there on each side, and adjust that. You can make a 3-band antenna out of that basic design. Isn't that cool? Okay, next is the fan dipole. It kind of has a bad reputation of a lot of interactions between the adjustments when you try to adjust the multiple bands. And there was some truth to that. However, a paper written by the Stanford Research Institute many years ago found that at least on the lower bands, if you separate the wires sufficiently at the feed point, you will have very little interaction between them. And I have a link here in this presentation. I think it's at hamuniverse.com that tells how to make it. But the fan dipole is still a great antenna because it has a low VSWR on all the bands, similar to individual dipoles. It has a 50 ohm coax feed, and it's amenable to a triplexer for like an 80-40-20 or 20-15-10 antenna. It also can be used in an inverted V configuration. So even though it's an old time antenna, it still works quite well, and it still has all its directionality in one direction for all the different frequencies. So it's nice in that regard. Another version of this fan dipole was written in an old ARRL antenna compendium. This was in volume 1. It was entitled A Great 10-40 Portable Antenna by Edward L. Henry. And I put a link into that antenna compendium, which is online. But this could be raised with a single person. And it's a multi-band antenna. It gives all the dimensions. And except for the poles, it fits in less than 1 cubic foot of storage and can be set up in less than 15 minutes by one person. So I think it's a really cool antenna. Okay, now let's talk about doublet antenna construction, which I covered earlier. It's basically a wire antenna with a center insulator and end insulators and lateral line of some sort fed by a wide range antenna tuner with balanced output. It must have balanced output. And then on the other side of it, you have 50 ohm coax going to the radio. So what are some of the advantages of a doublet compared to other multi-band antennas? Well, it's simple, low-cost construction. It's a great fail-day antenna if it's used by a single rig. You have reduced feed line losses. The ladder line or open wire type line has very, very low losses compared to coax at high SWRs. The feed line itself doesn't radiate, and so has less effect on antenna patterns. It's more immune to field-day interference from nearby antennas. And a nice feature is it's more immune to noise pickup. Coax is a lot worse for noise pickup than a balanced line. Easy to build. You have no interactions between many bands. You have no lossy transformers found in many commercial antennas. And at least for what's called the broadside doublet, the main lobe radiation is well behaved. It's in the same direction across 4 bands, and side rejection is the same direction on all bands. And I'll talk about that some more. What are some of the disadvantages of a doublet compared to other multi-band wire antennas? Well, you need a wide range balanced antenna tuner. It's not amenable for use with a triplexer, so you can't share it too easily with multiple rigs. Feed line hangs in the air from the center, which is mechanically not nice. You need 2 end supports, possibly a center support. Can be configured as an inverted V for easier installation. And as someone mentioned, lateral line losses are sensitive to rain and age. Rain affects the tuner adjustment, and that can be problematic. Open wire line is rain insensitive, so that's better. Now let's talk about what's called the dipole doublet. Well, that's what Cebik called it. In this type of antenna length is a half wave on the lowest frequency of operation. That's pretty well known and pretty common, and a lot of people use it. Its chief advantage are simplicity and the ability to cover all high frequency bands above the one which the wire is a half wave. However, it has some disadvantages. If the length is greater than 1 1/4 wavelengths on a given band, the radiation stops being broadside to the wire, and you start developing multiple lobes. And as frequency goes up, the number of lobes increases. It's usually fed with balanced line, driven by a wide range balanced tuner. or a single-ended tuner with a balun, which could be a 1-to-1 or 1-to-4 balun. 1-to-1 is actually preferable. The dipole doublet, here are some of the azimuth patterns. An 80 meter dipole doublet operating on 20 meters has deep nulls broadside to the antenna and 4 lobes almost 45 degrees off broadside. So you may think you're transmitting the way a normal dipole works, but you may be transmitting way off and you have a null where you think you have just strong radiation pattern. And as you go up in frequency, you get more and more lobes. So that's just something to keep in mind. The broadside doublet is different in that length is determined by the highest band and set to 1 1/4 wavelengths on that band. And it's actually called an extended double ZEP at 1.25 wavelengths. In this case, the lowest band is set 4 times lower than the highest band. It's approximately 33% shorter than a full-length resonant dipole, and there's little loss in gain compared to a full-length dipole on the lowest band. The low end is limited by low impedance and high capacitive reactance, making it difficult to match beyond 4-to-1. But the good news is, radiation is always in the same direction on all 4 bands. Off broadside rejection is the same direction on all bands. So this is the antenna patterns for broadside doublet. And you can see that from 40 meters to 10 meters. There are ears that develop, typical for an extended double ZEP at 1.25 wavelengths on 10 meters. But note that the main lobes are all in the same direction, and the off broadside is also in the same direction. Possible set of high-performing field day antennas: an 88-foot doublet for 80 through 20 and a 44-foot doublet for 40 through 10. There's minimal interaction due to non-resonant antennas, and each antenna is in the other antenna's off broadside nulls. Balance feed minimizes feedline pickup. What about inverted Vs? They're good antennas. They tend to be more omnidirectional. Off-center fed dipoles, a good general purpose antenna. Could be an inverted V or a flat top. End-fed half waves are one of my favorites. Operate multi-bands with a single antenna, only needs a touch-up tuner. Needs a common mode choke at the bottom. Good general purpose antenna. Could be used on 80 and 15 with a wide range ATU. Vendors that make good center fed antennas are Buckmaster, My Antennas, Palomar Engineers, Balun Designs. On the sweet spots for an 80 meter off center fed antenna, it depends on what bands you want to use. Can transformers at the top of an off center fed antenna be eliminated? Yes. You could feed it with 300 ohm ladder line with no transformer at the top. And then you could either feed it with a wide range antenna tuner or feed the bottom of the feed line with a 4-to-1 hybrid balun. The 50 ohm side goes to the 50 ohm coax to the rig. And there's recommended feed line lengths and so on. There were some simulation comparisons. I won't really go into that, but 014AA came up with a nice 40-20-15-10 flat top off center fed. It's like 30 feet high, 68 feet long. It's a good general purpose off center fed with low VSWRs. A lot of experts recommend using the shortest required length of odd 1/8 wave multiples at the lowest frequency of operation. This showed 132-foot doublet, 65 feet high, with 450 ohm ladder line, using the odd 1/8 wave formula for feeding length, 95.94 feet. And that was just an example, shows that works pretty well. Losses are pretty low, from 1/10 of a dB to 0.6 dB, pretty insignificant. Sometimes you want a certain length feed line as part of the antenna. An example is the ZS6B KW antenna, which is a sort of an optimized G5RV. I made an experimental doublet with tuned feed line. Doublet length is 41.4 feet, simulated an easy neck and sim neck. And that works pretty good, using a 300 ohm ladder line with a doublet length of 41.4 feet, about 35 feet high. Balanced antenna tuners is a complex subject. I'm not going to spend too much time with this. And I listed several different comments here. Owen Duffy has a lot of good stuff on his website. And I listed a couple of links for balanced antenna tuners. This I'm not going to spend too much time on. You want to balance on the input or the output. If the balance on the output, it sees a high VSWR with wide range of impedances. On the input, it sees a 1-to-1 VWR when the tuner is tuned. So there's lower stresses on the balun, but the feed line is impacted by antenna imbalance and tuner stray capacitance. Either one will work. Do you want a 1-to-1 or a 4-to-1 balun? In general, a 1-to-1 balun is the preferred choice to minimize tuner losses. Of course, nothing beats a good beam. So that's the story.
Thank you, Steve. Any questions or comments for Steve? Unmute yourself and speak up.
Yes, thank you, Steve. This is John.
Hi, John.
Yeah, it was there's a tremendous amount of information in your talk, and I guess we all have to make compromises in selecting the antenna, because depends on what trees you got on your property and so on. And then of course there's those that don't have any allowance for radios on their properties, and they've got to stealth them the best they can. But yeah, for doing, say, parks on the air, I mean, are we better off with some simple wire antenna, or you know, like a vertical and a quick radio on it?
Well, there's pros and cons to all of these things.
Exactly. I mean, I started off this hobby with a Carolina Windham, and I used that for quite a while until it got busted up, you know, by the storms. And then I had a vertical, and even that got busted up by the storms, but I fixed it a few times. And now I've just got a little screwdriver whip on my balcony here, and managed to get, you know, do DX100 in a year and a half with nothing much of an antenna on FT8, but voice, forget it from an apartment complex. So Yeah, you presented us all with a number of choices. I imagine each of us has one of those antennas in current use. And so, I mean, like WB1GRB, he has a Buckmaster. Now that's a trap antenna, right? And that's a completely different beast.
Yes, it's a Buckmaster. It's 10 through 80 meters, the 300 watt. And I'm using the MFJ antenna tuner, so I'm able to, it tunes automatically when someone connects to the remote. And they'll operate anywhere from 10 to 80 meters, plus 17 and those oddball frequencies, which it normally wouldn't cover, but it does with the antenna tuner, auto tuner. It works really good.
Yeah, there's lots of ways to skin a cat.
You know, one end is about, but according to Terry, he's the one that helped me put it up, is like 75, 80 feet. The other end's about 30 feet, 35 feet. It's like like a slope where it's sloped.
You can actually see one end of his antenna above his head right now. Oh,
And I did have RF on the shield, so I bought one of those MFJ antenna isolators, and it made a big difference. It got rid of a lot of noise, and I was hearing people I couldn't hear before. It was almost like night and day. And of course, I had to ground everything too, which I didn't have before. So I changed the coax. I did a lot of work to get this whole thing working properly.
Uh-huh.
All right.
So that's the story.
where is it?
Work there, a lot of work you did.
Good presentation.
Thank you.
Really enjoyed it, Steve. Just,
Dan Schaefer,
what's that?
what are you running in your backyard?
Well, it's so funny that this is very timely. I have the regular loop antenna that Terry helped put up last year, but I also have a G5RV, that ZB whatever W. It's 92 feet, and it came with the open window line, the 450. And what I did, instead of feeding it with coax, Steve, as you know, it comes with a connector for coax, and I guess it's 31 feet is the I forgot the length of it. And I just added a lot of I just bought 100 feet of ladder line, the open window, for my traveling purposes.
Right.
And boy, that's the 92 foot. And then I picked this up, an MFJ 901B, which is a portable tuner, for when I travel. It's really small, and that thing tunes. And I've been comparing it to my loop, and it is fantastic. I mean, it's, I don't use coax. I just use the ladder line, and it tunes. And then I also have 102 foot that WA2NAN built for me, which also uses the open wire ladder line, but I needed 100 feet of coax to get an SWR, but I'm just burning energy in the coax. So I basically cut off the coax and I put the ladder line on that one. And that one I can tune on to 160 meters with this little $50 MFJ tuner. I don't know if you're familiar with this 901B. It's got two capacitors and an inductor switch. So I love the doublets. I'm not crazy about antennas with the coax. I've gotten completely away from coax. So Steve, that was a very, very good presentation, and I appreciate that. That was, helpful to what I've been experimenting with to kind of see what it looks like in the charts.
Yeah. So that's basically the story. Over here, I use various antennas. Most of my antennas are end-fed half-wave antennas, which I like a lot. So if anybody has any questions on this stuff, I'd be happy to try to answer them.
Steve, just out of curiosity, because I travel a lot, and I have my vertical that I use on the beach, and that works great. But I also have these doublets. But tell me about, just a quick second, about the long wire. how do you feed the long wire antenna, and what transformer are you using?
Well, it's actually a resonant antenna, but I use end-fed half-wave type transformers that I've done a lot of work with.
To be like a 9-to-1?
It could be like 14-to-2 or something like that. I've used different transformers, different balance. So it depends. It's typically a high turns ratio type transformer.
And are you feeding that with coax or some type of a open wire line?
I typically, over here, I'm using end-fed half-wave antennas for most of my antennas, which has a high turns ratio transformer driving it. And they're resonant antennas, and they work on multiple bands. And I like the end-fed half-waves a lot because you can operate on multiple bands pretty easily. They're pretty forgiving.
So if I wanted to, when I travel, let's say, and I have a porch or a patio outside, and I want to do a long wire, say put out a long wire. If I want to get on 80 to 10 meters, let's say, how long would that wire need to be, and what kind of transformer? And I assume the transformer would be at the attachment to the railing of wherever I am, and the wire will go out to some tree somewhere.
Yeah, 80 meters is a little problematic when you're trying to operate portable, because it is a long antenna. It's about 132 feet long.
Mhm.
If you don't care so much about 80, sometimes you're better off with a 40-meter antenna, because that's only 66 feet long.
Mhm. But would I be feeding with that with a transformer or something, and then coax, or can I feed that with open ladder, you know, the window line, and where would be the counterpoise for that?
Well, if you feed it with a transformer, like if it's an end-fed half-wave antenna, fed with a transformer, that's fed with coax. The coax goes to the transformer goes to the antenna.
Mhm.
And that works pretty well. You could use open wire line or ladder line, and that will work well, but then you need something at the bottom of it. You need an antenna tuner typically.
Mhm.
So there's lots of ways to skin the cat.
Okay. I'll look into a little further. If I have any questions, I'll contact you.
Okay, sure.
Thank you, Steve. Appreciate it.
Okay. So that is the story. Does anybody have any?
I have a question.
Yes, Fred.
Yeah, years ago, I used to play around a lot with these programs. Now I've forgotten most of what I did, but I don't know if you were aware, I wrote a program that I think is still around on the internet for feedline analysis. And it would do a bunch of bands at once. If you gave the right information, you could see what your impedance was going to be at your end, and across a bunch of bands at the same time. It's been so long, I forgot some of the details. I do remember that most 450 ohm line is closer to 400 ohms.
Right.
And I at least it was back then. I suspect it still is, that the 450 is not the exact number.
Yeah, they typically are more like 400 ohms.
Yeah, that's what I found. But I was just wondering if you'd ever come across the program, because it would give you your impedance back at the transmitter end if you put all the right numbers in. And you could analyze and it was capable of doing a whole bunch of bands at once. Now, I will admit there's a little bit of a cheat. It would sort of assume that conditions were close enough that a linear interpolation between 2 points was not all that bad. Obviously, if you tried to do all of 10 meters, it wouldn't give you as good an answer. So 10 meters, you'd have to, if you want to cover all the 10 meters, I remember you had to break it up into a couple of pieces.
Right. That's true.
I think it's still on our website, by the way.
Uh-huh.
I haven't looked lately.
Yes, it is.
Yeah. And I did a search once and I found that there was a couple other places floating around on the internet.
Yeah. So
Well, I'm gonna download this new free version, number 7. Whatchamacallit? I met the guy at a hamvention out years ago. Turned out we knew somebody in common. It was one of those surprises. He used to work, I think, for Tektronix.
uh-huh. Okay, well, that's basically the story. I use end-fed half-wave antennas over here. I like them a lot. And I have two sort of at right angles to each other. So I don't know if anybody has any questions on it or that I could help answer.
There's our website with downloading links with the program.
Uh-huh.
Did you see it?
Yeah, I see it.
Okay.
Yeah, that looks about right. I haven't used it in so many years. I'd have to probably learn how to use it all over again. But it was an interesting project. And I even had to have the speed of light down to 4 significant figures or something like that to make it work right.
Uh-huh.
All right. So is there anything else for Steve, or can we let him go and end the meeting? Are we all pretty well good? If you think of something after the fact, send Steve an email, and I'm sure you'll get an answer. All right.
I'll be happy to try to answer any questions.
All right. So with that, I want to thank everybody. We're down to 11, but we had like 17 at one time. I want to thank everybody for joining, and I want to thank Steve again for his presentation. That I'm sure there was a lot of work went into that. And